So, to continue with our discussion, we were discussing various scenarios when means one flip flop is driving another flip flop through some intermediate combination circuitry, that how the setup and hold time and other delays, propagation delays and other delays, they affect the maximum frequency of operation of the circuit. Okay. So, we continue our discussion in that line. So, we look at global setup time, hold time and propagation delay to start with. You see, here we consider a scenario where data is delayed. That means, I have a flip flop, I have a combinational circuit, some inputs are applied, I am treating it in a global sense, not one flip flop driving another flip flop. Now, due to some reason x is getting delayed. So, let us see, this clock signal is like this. So, what are the requirements? The D input is coming to the flip flop. So, before this T setup constraint must be satisfied and this T hold constraint also must be satisfied. So, x, well, assuming that the delay of this network is 0. So, the data x must also be stable from here up to here, but because of the delay of this network it has to be stable a little earlier. Okay. T net. So, this is the ideal case where T net is 0, but when there is a finite delay of the network. So, we need D to be stable here, T setup time before the clock, but because of the delay of this network my x has to be stable at least this much time before that, and it should remain stable at least up to this much, because after that the propagation delay will take care of it, that data will reach here after Th. Okay. So, this is the constraint that needs to be satisfied here. So, TSU, as you can see, TSU is this plus maximum of T net, TSU plus T net, that will be your T setup time of this global input. So, the input setup time will be the delay of the network maximum delay plus setup time of the flip flop, and the hold time of this global input Th will be Th, the hold time of the flip flop minus the maximum, no, this will be minimum delay, because it is going in the negative direction, you have to take the minimum delay of this network. So, from this diagram these two equations are pretty clear that how these are coming. Okay. So, when you are feeding a data, so your data must be applied and kept stable at times which are governed by these two expressions. Okay. Now, if clock is delayed, so global setup and hold time is a single flip flop again. Now, clock is getting delayed, there is a delay element, it is getting delayed. So, your CLK input clock is this is without any delay, the CK is like this. So, in an ideal situation you must have this D input coming, setup time before that, hold time before that. So, for the input also, D also, this will be the setup time and hold time, but if this is delayed, this edge will get on the to the right. So, it will become like this, there will be a delay of Tc. So, what will happen, this D will get pushed here. So, the constraint will be TSU will be small TSU minus Tc, this will be TSU clock edge minus this minimum, and see, anything goes in the minus direction you will have to take minimum, anything going in the plus direction you have to take maximum, because for a general combination circuit the delays can vary. Okay, minimum path, maximum path, and for the hold time in a similar way it will be Th plus Tc, and because plus you take maximum Tc. So, for a scenario like this where the clock is getting delayed, you have to make calculations like this and apply the external input in this fashion. Now global propagation delay, again, say from a circuit like this, if there is a network which is driving, you have to take the output like this, then you have to sum up the delays of the all subcomponents, like Tc will be the delay of this clock, Tff will be the delay of this flip flop, T net will be the delay of this network. So the whole propagation delay will be sum of these three. Okay, this is simple. So when you have a path like this, so see, if your clock is delayed, your everything is getting delayed. So unless the clock comes, you cannot start the calculation. So your total propagation delay will also include that clock delay. So only after clock delay things will start, and you have to consider the other delays. Okay, fine. So this is to summarize the global timing parameters. You see here I am showing a general model of a sequential circuit. Okay, I am just explaining once more before going back to the slide. You see, any synchronous sequential circuit can be modeled like this. I can model it as a combinational circuit part. There will be several flip flops. So there will be some lines which are primary outputs, some lines which are primary inputs coming from outside. Some of the lines will be going to the flip flop inputs like this, and the flip flop outputs, they will be feeding this combinational circuit again, and there will be a clock that will be feeding all the flip flops together. So this is how you can model a synchronous sequential circuit. So every time a clock comes like this. So whenever there is a positive edge of the clock, so whatever is here in the output of the combinational circuit, that will get stored in the flip flop, and the new value will come here. So before the next edge comes, this new value will be used to calculate the new output, and when the next edge comes, that new output will get stored again. So in this way, cycle by cycle computation is going on in the sequential circuit. So this is a model of a synchronous sequential circuit. Okay. Now coming back to this diagram, let us see, here we have that kind of a combinational circuit and flip flop, that sequential circuit as I said, and we are assuming that the clock that is fed also incurs a delay here. There can be a delay Tc here, and each of the flip flop is incurring a delay of Tff, and this combination logic network is incurring a delay of Tn. Okay. So the timing requirement will be like this in terms of globally you want to see, because x is a global input. So T setup time, like here diagrammatically it is shown here also. So when the clock comes, this Ck is getting delayed by Tpc, is getting delayed, and when this Ck comes, this is feeding the flip flops. So the D inputs of the flip flops will incur the setup time. Minimum you have to be, this is the edge, so this is the setup time minimum, and after that this is the hold time, and Tpn is the delay of the combinational network. So this setup time of x must be Tpn time before that, and here also similarly there will be a hold time. So the setup time will be this TSU plus the delay of the network minus this delay of this TPC, delay of this clock network. This clock network is getting delayed because when clock is getting delayed you subtract, and hold time also there will be similar calculation, and Tp, the total propagation delay, the sum of the propagation to the flip flop, the combinational network and the clock. So this is a summary of whatever we discussed in the means earlier slides. Same thing is summarized here. So, if you have a circuit like this, so with respect to the global parameters, the input, so what will be the setup and hold time with respect to the inputs and how you can calculate that. Okay. So, with respect to the clock edge, so how much before you have to apply x, and after the clock edge comes, minimum how much you have to keep holding the value of x. Okay. These are important. All right. Fine. Here we have an example where we are trying to find out the setup and hold time for the input signal load relative to the clock. This is an illustration of this same case, just a specific example. So, here the combinational network consists of 3 levels of gates, okay? One inverter, one stage of NAND, another, this is also NAND gate, one stage of NAND. So, the setup time will be, you see the setup time was what in the earlier slide? This was the expression, right? T setup plus max Pn. So, with T setup, this we are using this equation, max propagation delay minus delay of the clock. So, max network minus delay of the clock. Max network means what? Max of an inverter, max of a NAND, again max of a NAND, and clock is only an inverter minus min of an inverter. So, this is the setup time of the global input load. Similarly, hold time similarly can be calculated. This was the expression, and min T net will be the same thing, inverter NAND, and minimum delay is what? This was the max delay. Min delay will come from here. This was the max delay, okay? Not NAND and NAND. Min delay will come from this path, NAND and NAND. So, only NAND and NAND are there, and max DC is this. So, you can calculate TSU and TH of the load signal with these expressions, right? Okay. Now, here there is the illustration of a case which is very important. Sometimes we want to use a load control of a flip flop, like a clock is coming, but not always we want to load the data into the flip flop or the register. So, whenever we want to load, we will activate a load signal, only then it will load. Some of the register or flip flop can have a separate load control input, which you can use if there, but suppose it does not have, it only has D, Q and clock. So, how do you control the load? So, there are a few alternatives we are exploring. So, the first alternative is what I am saying is that this load signal we are using an AND gate to gate it with the clock signal to generate the clock of the D. But what I am what you see is that this is not a very good idea. Why? You see, the clock signal is coming like this, okay? The load signal will be active sometime, suppose it is high like this. The CK signal for a single clock cycle, you see that CK will be active twice. But actually what you want that for one clock period, the CK should come only once, maybe this second time, this one, this should not be there. So, if you gate it like this, depending on when you are making load high and when you are making load low, your number of clocks generated may be wrong, okay? Maybe 2 times. So, there is one solution first we suggest. See here, what we are doing? We are activating load here when the clock was high, we are doing that. Second time what we are saying, we are making a constraint, we are restraining load, we are saying that we can activate load only when the clock is low. That means, we are activating low only when the clock has reached low. Then you see the first pulse will not come, only the second pulse will correctly come, okay? But only if there is a clock skew, then there will be a problem, because these edges can be moving forward and backward because of skew, but otherwise we have solved this problem, right? But again, here is another solution which also avoids the problem irrespective of when you are activating the load, that instead of using an AND gate, you use an OR gate and you invert the load and apply to this OR gate. So, you see, if you apply load like this, so you are making it high when the clock is high itself, like in the previous example, and if you calculate the output of this clock, it will come like this, a single pulse. The first pulse will not come. So, there can be clock skew, but only one triggering edge per load pulse. So, at least here also we have solved it. But what designers say is that these are okay, you can overcome the problem by doing a lot of tricks like this, but the best way to handle this is to use a circuit like this, because you see, tinkering with the clock input is highly, you can say, this is something which you must not do or should not do. Here we are introducing some circuitry to the clock input to feed the clock through some other circuitry, but what people are saying is that this is not something which is good. You should not play with the clock should go directly to the clock, but rather you use some extra circuitry to handle this problem. So, what is this extra circuitry? This is nothing but a 2-line to 1-line multiplexer. This multiplexer has two inputs, one is the D input, other is that Q output, that is also coming as an input, and load is the select line. If load is 0, then D is selected, that means you are loading. If load is 1, then Q is selected, which means no change. So, whatever was stored, that same value will get stored again. Okay. So, this is a very safe way of incorporating the load feature in a flip flop which does not have a load input, right. Okay. So, let us look at a few examples here. So, where we shall just illustrate some timing violations in 3 cases, whether there are any. Let us look at a scenario. There are 2 flip flops. The first flip flop is feeding to some combinational circuit that is going to the input of another flip flop. There are 2 separate clock inputs, let us call them CLK20 and CLK10. The hold time are 1.5 nanosecond, let us say. So, what we are trying to explore is to determine whether there are any timing violations, and delay of this combination logic is minimum 5 nanosecond. So, here let us work out. So, the first thing is that let us say the minimum data path delay in this case is 5 nanoseconds. Maximum clock path delay, so we are not assuming any skew, so 0 nanoseconds. So, let us call it hold slack, the separation between these 2 delays. So, how much difference is there? 5 minus 0, this is 5 nanosecond. Now, if this is positive, we can imply that there is no timing violation. This you can think that why. So, here we are looking at 2 things, minimum data path delay and maximum clock path delay. Look at the circuit once more. Minimum data path delay is this one, data path is this one, 5 nanosecond. Clock path delay, we are not assuming that there are any skews here coming together. So, the hold slack will be data path delay minus clock path delay, that is 0, because you can just compare it with another case. Let us look another case side by side, the case 2. Here we are saying that in addition to that there is a clock skew of 3.72 nanosecond. So, here what will be the calculation? Side by side we are showing minimum data path delay. So, here also will be 5 nanosecond. Maximum clock path delay because of the clock skew, it will be 3.72 nanosecond. Hold slack, you see there is a hold time for clocks. Because of the clock skew, that hold delay will also come in. So, this will become 5 minus 3.72 plus that hold time 1.5. This will be minus 0.22. This is coming negative, which means there is a timing violation. So, in this second case, so if there is a clock skew of 3.72 nanosecond, you cannot satisfy the timing requirement anymore. There is a timing violation which is coming in. Okay. So, lastly a third case. So, here we are showing some additional delays in the clock network. Suppose there are a delay of 4 nanosecond in the first clock network, a delay of 2 nanosecond in the second clock network. So, in this case let us similarly work out the delays. So, in the first case it is delayed by 4 nanoseconds. So, it will be 5 plus 4, it becomes 9 nanoseconds. Second one, there is a delay of 2 additionally. So, it would be 3.72 plus 2, which is 5.72 nanoseconds. So, this calculation how it will be now? It will be 9 minus 5.72 plus that hold time of 1.5. This comes to 1.78 nanosecond. Because this is positive, here also there is no timing violation. Right. So, these 3 examples actually tell you that depending on the scenario, if you are given the data, then you can play around with the data and make simple calculation and comparison and find out whether you are violating the timing requirement anywhere or not. Okay. So, you can see clocking is not a very trivial issue. Calculating or just evaluating whether for a certain scenario, for certain delay scenarios, your clocking will give you correct operation. You have to understand the clocking issues very clearly, and we have to check whether all the constraints that are supposed to be satisfied, they are getting satisfied or some of them are getting violated. Okay. So, these are something that you need to do. Then coming to the metrics for clock design. So, when you are designing a clock circuitry, there are a lot of issues that you need to look at. Now, actually some of this we will be addressing later in our later lectures. Of course, the total power requirement. You see, clock is a network which is heavily active. There is signal transitions at every cycle, and for any CMOS circuitry, you know, whenever there is a signal transition, there is a dynamic power dissipation. So, clock power dissipation is one of the heaviest power hungry networks inside the chip. Okay. Skew, jitter, maximum skew, maximum jitter may be some metric that you may want to just enforce. Flexibility of the distribution says, can you add additional clock leaf nodes, which means you are changing the clock loads, means at any time in the design cycle, because it may so happen that if you want to make some modification, some skew values are changing drastically. So, you may have to redo or redesign the whole network. It should not be like that. Okay. Flexibility should be there. So, how much duty cycle variation it can tolerate, and of course, reliability. Because of large current flows, there should not be some variation in the physical properties due to electromigration, which might lead to wrong operation. So, most of these metrics are mutually conflicting, they have to be traded off, and of course, for a particular scenario you have to look at which one is the most important issue for you. For some application, power can be the most important issue. For high performance circuits, skew and jitter can be very important. For programmable devices, maybe flexibility of distribution are important. So, there can be mutually conflicting issues. Okay. Regarding clock power dissipation, I just now mentioned, the clock signal switches continuously twice every cycle, one from low to high and high to low, and it can consume up to 40% of the total power of the chip. Okay. So, this is a quite major issue. So, if you can implement a clock tree that consumes low power, this can also imply that a chip will be a low power chip. So, the power consumption will be having two major components. One is of course the dynamic component. Depending on the frequency of switching f, the power will be given by the capacitive load, square of the power supply and the frequency. Okay. So, the watts of the distribution, the clock buffers, they will determine CL, the flip flop loads, they will all determine the capacitive load. So, if you can reduce the capacitive load in some way, your power consumption can decrease. Then of course, short circuit power, when during switching for very short duration both the PMOS and NMOS networks in a CMOS gate are on and there is a short circuit power. This is called short circuit power. And of course, overall chip power can be reduced by switching off some portions of the chip when it is not required. This is called clock gating. Well, again we shall be talking about this much later. This is another aspect of clock design. Solving the skew problem, there are a few rules of thumbs you can follow. Careful design of the clock buffers and wires, we shall look at some of these later. Make the design electrically symmetric, as I had said, and should not be too much dependent on temperature and process variations. Okay, and also change in load, it should be that way. You can use some special circuitry which can detect skew and automatically do some compensation, some feedback circuitry based on phase lock loop or something like that. So, you can have an explicit circuitry for that, and you can also have a delay aware synthesis or timing aware synthesis, where it can explicitly look at the skew problem and do some kind of clock tree synthesis that controls or limits skew to within a tolerable limit. So, with this we come to the end of this lecture. Thank you.